So, we saw the movie, we listened to the lecture, we learned about the book in the right order. Because, at least from my point of view, the movie is just a wonderful, wonderful teaser for the book and the lecture. And we learned here from Kip himself that to really understand the movie, you have to read the book, which was prepared confidentially and published almost secretly. And I can assure you, I saw the movies, I read the book. After you read the book, the movie is, well, you can skip it. And then I was asked by our host to lead this question and answer section, and I was asked to ask Kip some questions myself and then to give the audience chance. So I prepared some questions, and my only worry was that what amount of the answers will be covered by the lecture. Well, the first third of the lecture was just answers to my prepared questions. Well, but there are tiny bits which are still there, so I'll try to ask about these bits. I tried to focus on a tiny part of the movie, which is very, very rich from the point of view of physics, and that's the Miller planet, the water planet which you started. The first question or ask for comment is that Christopher Nolan needed this planet for this enormous time loss. As you showed us, you cannot reach it or even come close to it with a Schwarzschild black hole. You have to have Kerr black hole, rotating almost very, 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 very close to the maximum possible rotation, maximum possible spin. And the Gargantua had this spin, which is quite improbable, which is not good for the story to have very improbable things within. However, as I learned from your book, The Science of Interstellar, you personally showed in a scientific paper before that you cannot get very, 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 very close, but only very close, which is 1.98 of the maximum and no 9.1999999. So the movie is scientifically correct, but with a grain of salt. Is it right?
With a grain of salt, in the sense that, so this is one of my very early technical papers that I wrote in about 1973, I think. And so if you have a black hole surrounded by this kind of a disk, a thin accretion disk, as the disk, as the gas flows into the black hole, it speeds up the spin. And if that was the whole story, you could fairly quickly go all the way to the maximum spin. But in fact, the black hole then acquires, as it's spinning very rapidly, it has a cross-section, an ability for capturing radiation that spins it down, that gets much bigger than radiation that spins it up. So the gas itself continues to spin it up, but the radiation, the light coming off the black hole, it gets captured by the black hole, some of it, in such a way that it slows the spin down. So if if an advanced civilization wants to build this kind of a black hole spinning this fast, they're going to have to prevent the radiation from falling onto the black hole. And I mean, that's implausible, very implausible. And so from that point of view, I had already in 1973, I think, had proved that in the real universe with radiation from the disk falling into the black hole, this won't happen.
Yeah. Okay, so the Gargantua, in fact, is impossible.
It's impossible unless some advanced civilization prevents the radiation from falling out.
Okay. Then the next question, which was already answered, but I want to put a stress on it, that such amount of rotation of a black hole would deform the image to extent which Christopher Nolan did not like.
Yes.
So, in spite of correctness from the scientific point of view, what we saw is not the black hole spinning as fast as Gargantua should, but only, if I remember it correctly, 60%.
60% of the maximum. That's
okay,
right.
So Nolan's insisting on this extreme time loss causes problems which he avoided just by using.
Yes. So there were compromises made. As I said, Nolan's goal was to make a great movie, but his goal was also to do so in a manner that an audience that knows nothing about these technical details will still find, will not be disturbed, will not be deeply puzzled by what they see. And he has some sense, some very good sense, I think, of what's acceptable for a general audience and what's not. It is remarkable how much he allowed in terms of wild things that were based on real science and went along with. But these were issues that we discussed at length, and we agreed on these things. The only thing that was really seriously different from how it would really appear was that trip through the wormhole. These other things are more mild, at least in my view, than the trip through the wormhole.
I think that's the reason why the wormhole is opened near the Saturn, so that the audience see the Saturn with a ring, and then the ring around the black hole is somehow similar, so they are used to it, but they are used to circle shadow of the circle Saturn, and they would expect circle shadow of the black hole, so that's what, Then there is another question. I heard an interview with Jonah Nolan, the brother and the screenwriter, where he said that yes, the ring around the black hole, we see the half of the ring, and then we see it above and under the black hole. And he said, if I remember it correctly, this is because the ring is deformed by the gravity, which sounds like if he thought that it's the ring which is deformed, as we saw in the lecture. It's just the image, because we see the ring is just as a Saturn rings, but the backside we see from the up and from the down as Now, maybe it was just misunderstanding, but maybe Jonah really thinks that the ring is deformated. So the question is, how deep do the Hollywood people really understand you?
Well, I think by the time I finished with him, Jonah understood things fairly deeply. Okay. And I think in this case, it was a slip of the tongue. The image is deformed. But he didn't understand things nearly as deeply as his brother Christopher Nolan. Chris came in already. Well, so an example. How did it come about that we decided to bring Cooper back in the Tesseract back to Earth? And so Chris said to me, I want to bring Cooper, I cannot bring Cooper back through the wormhole again. We've already seen the wormhole trip. I need another way to bring him back. He said, so I would like to bring him back faster than the speed of light. And I said, you can't do that. He said, go do a real calculation. And I said, I don't need to. And so after about a week he gave up on that idea. And so he said, what do I do? And I said, well, you put him on the three-dimensional surface of a four-dimensional sphere, which is a spacecraft that goes up into the bulk and back. And he said immediately, no, but I will use a tesseract instead. And so he knew about tesseracts. He knew that going in the three-dimensional face of a four-dimensional cube was, he thought, and I think absolutely correctly, it was a much better idea. And that was his idea. He actually knew a lot about tesseracts before we even started, because he'd thought about this. He'd been exposed to them initially in a child's science fiction book called A Wrinkle in Time that had a tesseract in it. So Chris certainly didn't understand these things at the depth of a physicist, but he understood them much more deeply than anyone else that I dealt with in Hollywood, except for Anne Hathaway. And Anne Hathaway, we had a conversation before she started to film in which she wanted to understand some of the science better. But the first thing when we met on the phone, on Zoom, because she was, no, maybe it wasn't even Zoom, I've forgotten. Anyway, we met on the phone because she was out of town. And so she began the call by saying, I'm a bit of a physics nerd. Can you please tell me, do you as yet have any good observational or experimental data about the laws of quantum gravity? And that's not a question that I expected to hear from Hollywood. So she was fairly deep in the science, and Christopher Nolan, a little less deep, but that didn't matter because I had such a very good communication with Chris. And we trusted each other, and we talked these things through, and Chris knew how to ask questions or challenge me in ways that made me think, as I've indicated. And so working together, we were able, I think, to achieve something quite remarkable. I would say of this film, setting aside the things that we've talked about that I focus on in the book, the amount of science in this film is enormous. As people who have seen the film 10 times, as some of you, I gather, have, every time you see it, you see things that you missed before. This is true generally of Christopher Nolan's films. It's true of Oppenheimer as well, for example. And he has this amazing ability to make a film that can be viewed at many different levels. And it can be enjoyed at the level that is fairly superficial, or it can be enjoyed at a level that is far, far deeper.
Yeah, my favorite, the Christopher Nolan is master of hiding things in such a way that some of them are not visible, not after 10 times, but they are never visible. And my favorite example from your book is the data while other members of the crew are on the Miller's planet, the one which is on the spaceship is doing some measurements of the resonant frequencies of the black hole, yes. And he's reporting about them. Then he's trying, and they are They are visible, but they are completely hidden. Can you comment on that?
Yeah. So he has a table of the measured resonant frequencies of the black hole's vibration, and there are one or two that are wrong, but they're wrong in strange ways that he identifies as gravitational anomalies. And so these are things that, in agreement between Christopher Nolan and me, that I made these tables up, I think, together with a student of mine, and that was there, and it appears in the film, but you will never see it, as you say, unless you're told to go look for it.
You said that the notebook with the tables is on the table somewhere, but that's it. Okay.
But I've forgotten whether he opens the book up or not. But there are a number of things like that were props that I helped make that made that enabled them to film in ways that they may or may not use these things, but they're there and available.
Yeah. Another thing concerning the Miller's planet, and then I will finish this part, is that if you want to get to the Miller's planet from the parking slot of the spaceship, you need to go towards the black hole and then back to the orbit. There is no hope to have enough fuel for that, so you need the gravitational slingshot, and as I learned from your book, 2 intermediate black holes are needed for that. Nothing like this is shown in the movie. There is not understandable.
Well, so in the movie there is a line that this is something
about
we discussed. So in which Romilly, I think it is, says, maybe Romilly, maybe Tars, I'm not sure, says we can do a gravitational slingshot off of this neutron star. Now, you really need a black hole for the purpose, but Chris said, I don't want to confuse things by having more than one black hole discussed at the same time. That will be too confusing. So he said, we'll compromise. We'll have them talk about doing a slingshot off a neutron star. But that line is in there to basically give the indication that to get to Miller's planet, they had to do slingshots.
Yeah. And the very last question, from the Miller's planet, for a moment, the Gargantua is visible, but in a way, as you pointed out in the book, we wouldn't see it on the planet. It's too much small, and also the ring is visible in a way it couldn't be visible from the planet because it's too close to
but from the planet, the sky is all clouded up, so you don't see from the planet itself. You don't see the black hole.
But I think that's
you may see it as they're nearing the planet. I'm not sure, but if you look while they're on the planet, I think
okay, maybe I'm mistaken. I think that there is a shot where the
well, I could be wrong too.
Black hole is on the sky somewhere. Okay, I'm taking back the question.
Well, if there is, then I missed it, and it might be wrong, but I was pretty sure that
I would bet I am wrong.
That the planet, the sky was all completely clouded up, so you don't see the disk or the black hole from the surface of the planet.
Mm-hmm. Maybe when descending?
Maybe when descending, it may be.
Okay. Now the mic is going to the audience. I don't know if we may switch the line.
Yeah, could you turn up the lights up on the audience so we can see?
So the floor is yours. If there are any questions, there should be 2 mics in the audience. with legs, Mike with legs.
Hello.
Yeah. We can't see anything. Is it possible to get more light out there or less up here? Oh, that's much better. Okay, good. Thank you.
Thank you very much for your lecture and also for a discussion. I am absolutely clueless about physics, but still it was very interesting. And but what was interesting for me is it sounds to me, and maybe it's not correct, but as if we can get some scientific progress by combining high-level research with people who are basically, I don't want to say ignorant, but not that deep in the issue, by asking questions which are unorthodox for people who are too deep, which might be also somehow a recipe for making scientific progress in more general. So I don't know, either we make more movies about different scientific questions or something else, but this is what I take out of it, and it seems to me a very interesting thing to think about. Thank you.
Well, I've had two collaborations where collaborators who would ask questions that would really challenge me. One is with Christopher Nolan, the other is with Leah Halloran, the painter, where we've published a book about a year ago that is her paintings and my verse, my poetry, trying to convey the essence of things related to the warp side of our universe through tightly coupled paintings and poetry. And I have, from that experience with these two people, I have come to appreciate how somebody who's very intelligent and very creative can ask very interesting questions that made me think about things in a different sort of a way. I think maybe among these, so mostly these things are things that trigger me to have new ways of expressing, of describing science to non-scientists. That's mostly what I get from this. But is some, like what you say, and so the best example I have is the movie Tenet, which is another Christopher Nolan movie that I consulted on. I was not deeply involved in it, but in the movie Tenet, he has people who are moving backward in time relative to the rest of the universe. And that means that the direction in which they see time flow is opposite to us. But the direction in which they see time flow, as Christopher Nolan knew before he and I started discussing this at all, is the direction in which entropy increases, randomness increases. And that really is the thing that gives us our sense that if I throw a glass on the floor and it breaks, that's normal, but you never see a glass on the floor pull itself back together and sit on the table. That doesn't happen. It could, but the probability is exceedingly small. And so that gives us our sense of direction of flow of time. And so he brought me on board to discuss this when he was just starting to work on this movie, because he wanted to see if I, as a physicist, could give him any interesting thoughts about this. And what this really intrigued me about this is not something I'd ever thought about, but at the interface between the person who's going backward in time and the rest of the universe, atoms, molecules that find themselves at the interface, they don't know which direction randomness should increase. And so the laws of physics at that interface are really interesting. And it's an interesting question in what we call statistical mechanics. What would statistical mechanics look like in these circumstances? And I think one could, I've not taken the time to do this, but I think one could have a lot of fun as a physicist trying to work out statistical mechanics in this kind of a universe. But what I did tell him is it would be best if you put the people who are going backward in time in some sort of a rubber suit or some sort of a suit it gives them a sharp interface with the external universe so that their skin is not interacting with air, and they need to breathe air that is going in the same direction in time as they are, so they need to carry their own oxygen supply. And so that's what he does in the movie. That was my big contribution to the movie, was the rubber suits and their own oxygen supplies. But Nolan's contribution to me was, this is really, we've never seen this occur in our universe. It may well be that the laws of physics forbid it, but I don't see why they necessarily do. And I think it is a wonderful, challenging problem to work out the statistical mechanics, the mathematical laws of physics, how they would behave under these circumstances.
So the answer was affirmative. Yes, you need to make more movies like Interstellar and Tenet. Other question, please?
I'm sorry to go on and on, but I get excited by that. And so that's the answer, that he made me think in ways that triggered me to think about physics, aspects of physics that I've never thought about before.
Hello. First of all, I would like to thank you for this discussion. It's an honor to meet you. And my question is kind of related to the film where humanity faces a chance of extinction. And so if you have some kind of message, some kind of line for humanity, for future, so we don't have to face such a chance of world ending, and if there's something you want humanity to remember. Thank you.
Tough question, but...
Well, so let me tell you what we did about this question. So it was Jonah Nolan's idea that they would... that part of the movie, the early part of the movie, was basically Jonah Nolan's contribution. And he said, it's a dying Earth, and so we had to have a discussion of in what way is the Earth dying. And so we did what we had done in several other occasions. We brought together the best experts we could find in the relevant physics, or biology in this case. So we brought together real experts on things like biological catastrophes, and we had a gathering then of about 6 or 8 biologists, biomedical experts, including, I think, a couple of Nobel laureates in biology, and we met at the Caltech Faculty Club. We bought them some very expensive wine and got everybody relaxed with wine. And this was Jonah Nolan and me and Linda Obst. We set up a recording device at the center of the table, and we had a 3-hour-long discussion of what kinds of catastrophes could occur. And many ideas were thrown out, but what we wound up with is the catastrophe that we chose to be the backstory is this, that is a blight, and the word blight is used in the movie. A blight is a disease of plants that kills plants. And the biologists tell us that there are 2 kinds of blights typically. There's a very lethal blight that kills everything it encounters, but it's very specific to one plant species. It says narrow in what plants it attacks. And then there are generalized blights that can attack many different kinds of plants, but they're not very lethal at all. And of course, it's natural that those are the kinds of blights that occur, because if you have a very lethal generalized blight, it could destroy all the plant life on Earth and we wouldn't be here. And so the proposal was, and this is what we went with, that a generalized lethal blight has occurred. And the biologists told us we don't know any reason why that couldn't happen. We've never seen anything like it before. But, and so that became the backstory. But we had many other possible backstories that are related to climate change and so forth. But that's what we chose in the end, because it was something that could happen on the rather rapid time scale of that we're dealing with of a few decades.
Well, I'm afraid I may be mistaken. I'm quite frequently mistaken, but I'm afraid that the question was not about what the possible dangers are, but if you have some punchline to avoid all the dangers. I'm rather skeptic, but I'm afraid this was the question. Am I right?
Yeah,
Okay.
so my answer to avoid the worst dangers, get rid of Donald Trump.
Among others, among others.
Among others, among others.
Another question, please.
Hello. I'm still a little bit puzzled by this whole traveling in time, specifically two aspects of that. Like, I get how this tesseract travel like gets you very quickly out of space through the through the bulk. But like interfacing with the brain, does the physics suggest we could be interfacing like back in time? And then the second thing which really bothers me is like this causal time loop, right? Like things that have been done in the future kind of make that future possible in the first place. Does physics say anything about that?
Yeah, so these are questions that I spent a lot of time thinking about in the late 1980s. And as did other people. And actually this was generated by Carl Sagan's movie Contact, novel and movie Contact, was the thing that triggered me to start thinking about this, and then I triggered colleagues to start thinking about this. And so we wrote a handful of technical papers on these issues of causality. As far as I can see from the work that I and others have done, and that was largely done in that era, the laws of physics can deal with backward time travel in a self-consistent way. But it requires, in some cases, going all the way to the quantum domain, and you may not be able to do it in some cases classically with classical physics, but the quantum fluctuations play some key role in this possibility. And it was Jim Hartle using a variant of quantum mechanics that was devised by Richard Feynman, called the sum over histories quantum mechanics. And he and Murray Gell-Mann developed it further, and then Hartle used it to basically show that you really can pose initial data, you can evolve then through space and time, even if you have backward time travel, and you can do it self-consistently. But you get some weird things happening, like if the backward time travel is only at some point in the future, you start knowing before you reach that point in the future that something weird is going on, because the statistical properties of things start showing up. So anyway, the bottom line is this is an issue that I think is a very interesting issue in the laws of physics, an issue with which I and others have struggled, and an issue where if you adopt Feynman's approach to quantum theory, it appears to me that we can perfectly well live with backward time travel. As physicists, that may not mean it be pleasant as human beings, but.
Okay, I would like to correct myself to your sentence that first of all we have to get rid of Donald Trump. I remarked among others. I would like to be more specific, among other. Okay. Another question. We are slightly ahead of time, but unfortunately the number is negative. So we don't have too much time, but yeah, please.
Professor, thank you for being here. It's a privilege and honor. Now, in 1984, they made a movie called Terminator, and at that time it was pure science fiction. Over time, over the decades, it seems that most of the technologies, apart from maybe time travel, have become reality. You have made, or Interstellar was made 2014, if I'm not mistaken. Will we see the practical application of gravitational distortion or technologies in this movie in, if I'm counting well, mid-century? Thank you.
I think that's probably a little bit too soon. It depends on which of these things. So let me say what I do think we will see by the mid-century, which is not actually in Interstellar. By that point, I think we will have observational data from gravitational wave detectors about the birth of the universe that tell us how the universe was born and what these laws of quantum gravity are. So the question that Professor Brand and Murphy Cooper are trying to get at, what they call the professor's equation, I think there's a pretty good chance that by the middle of this century, roughly the middle of the century, the time frame 2050, 2060, 2070, we will have the answer to what those laws of quantum gravity were that controlled the birth of the universe and that control what goes on inside of black holes. So, thank you very much. But that's about all I can speculate on. But that is one thing that I've thought a lot about, and I know what technology is required in order to see these gravitational waves, and I think the necessary missions are likely to fly by that time scale.
When the time is running out, there is a standard phrase which I hate, so I'm not going to use it, but I'm going only to remind it that are there any 2 or 3 important questions? Please.
Thank you very much. I got 2 questions, but they are very, very short. First one is the slide forces towards the movie. First one is the slide forces in the black hole. They are strong enough to break the ranger, however, Cooper survives. Is there any logic behind it, or
yes,
is it fiction?
The larger an object is, the more easy it is to tear it apart by tidal forces.
Okay.
The tidal forces are proportional to the size of the object. And so the Miller's planet is strongly deformed, but the people don't feel the tidal forces at all. And the Ranger spacecraft can be torn apart, and Cooper probably feels the tidal forces, but not to the point that they injure him.
And the second one...
Sorry, I don't understand the answer. In fact, the breaking takes place at the level of atoms and molecules. So I would guess, incorrectly probably, that the tidal forces are the same at these distances. So I'm definitely not saying that your answer was incorrect. I'm claiming I don't understand it.
So the breaking of a solid object occurs at the point where it does because of defects in the structure. If you had an object, say a crystal, that was a perfect crystal, it would be able to withstand strains of a few percent. But the breaking of a normal crystal occurs at strains of a few tenths of a percent because of defects, crystal defects. And and so in some sense it's not, it's due to macroscopic aspects of the structure.
Second very short one is the astronaut that stayed on the orbit of the Gargantua and measured the resonant frequencies of the black hole cannot send a signal throughout the wormhole back to Earth, if I remember correctly. That comes to me a little bit fishy, because in the previous scenes we could see that side of the universe through the wormhole. And since the waves are still electromagnetic, so I don't see, so is there any logic behind that one, or? Yeah,
well, there are various possibilities, and that's not an item where we really specified the answer, but the kinds of possibility is this, that if he wants to send a signal through the wormhole and back to Earth, once it goes through the wormhole, it will be sending it with radio waves. And the diffraction is such that he's basically going to need an amplifier on the other side of the wormhole to get the signal strong enough to get it back to Earth. It's not like sending it through free space, but he's got to send it, and the wormhole will capture a piece of the signal, but then once it gets through the wormhole, it'll spread. It will not be well focused. It won't be well focused, and so you basically have to have an amplifier. And there is somehow, if they had a transponder, call it, if they had a transponder, it's malfunctioned, for example.
Yeah, maybe. As we learned in the movies, maybe love is some kind of another force or something. And if that is true, I'm pretty sure that the purpose of drama, which Christopher Nolan is a master of, will also be another force, and this is forcing this answer or another answer for your question.
Yeah. Thank you very much.
Yeah. Let me just make a remark about love.
Yeah.
So in the movie, I've forgotten who it is. It's maybe it may be Amelia Brand. I'm not sure who it is. Makes a remark about how love can cross dimensions, and there's a columnist for the New York Times named Brooks who loved Interstellar and wrote a column in which he focused on this line and love and how important it was in the movie. But if you look at the index of my book on the science of Interstellar, you will not find the word love there. That says something about my attitude toward that line in the movie.
The last two questions, let's make.
Okay. Good evening, everybody. At first, I didn't want to ask this question because I was hesitant, but a few minutes ago, you mentioned entropy. So my question is, this movie Interstellar, it's supposed to inspire us, normal people, to pursue our lives in the way of science. So do you see a way in the theory of entropic gravity? Like, is it the right way to focus ourselves, like the humanity? Like, should we, or like, is it, like, what do you think? What's your opinion on entropic gravity? And the second question is, will there be a sequel, like Interstellar sequel? Like, will you catch up with Chris and like get us what we all want?
Well, the second question is easier than the first one. Chris decided very early that there will never be a sequel.
Okay.
And I think he didn't say it this way, but it's pretty clear to me, watching the movies he's made, that he is at least in these later years of his career, middle to later years, he wants to make a variety of different kinds of movies. He's made a movie like Interstellar, he's made Interstellar, and I think he just wants to do other kinds of things. But the thing that he told me after, a few months after the movie came out is that there were not enough unresolved issues to be a foundation for a good movie. And if he were to make a sequel, it would have to basically raise a whole new set of issues because the issues so central to the movie were most all resolved. And with regard to entropy, I don't quite understand your question.
I can maybe explain.
Yeah.
In 2012, Eric Verlinde published a paper, a study about entropy gravity, theory of entropy gravity, where he states that entropy should be, gravity should be an entropic force.
Okay, so this is a particular topic that I've not studied enough that I have an opinion on.
Okay, that makes us do. Thank you very much.
Yeah, okay.
Okay, did you notice how smart the audience is since I tell them that only 2 or 3 questions are available? Every question is a double question. So the last question, and it cannot be triple.
Yes, and I maybe hope that it's a good closing question, because I would continue the line of questioning started by the colleague here, and that Interstellar is both a movie that starts pessimistic with the vision of dying Earth, but ends with our hope among the stars. But it seems to me that nowadays in art, the pessimistic vision prevails, and even in science with the talk of reversing growth and progress, while in the past, physicists had grand visions like Freeman Dyson or Gerard O'Neill's space habitats. And my question is, what is your stance? Can we be optimistic? How to revise these grand visions that maybe were recently hijacked by wrong kind of people?
So I'm very optimistic on long time scales. I think we have periods when there's some retrenchment, when things turn sour for a while, and it's true it can happen in physics as well as in political life or everyday life. But at least based on my understanding of human history and my own personality, I'm a real optimist on long time scales. So let me turn specifically to physics. When I just finished my PhD, I moved to Caltech as a postdoc, and as a postdoc, I was coming into a great institution with absolutely superb students, probably the best set of students in the world, physics students. But it was at a time when physics, theoretical physics seemed to be rather dead. It was a period when there was not much interesting going on in what was called high energy physics or elementary particle physics. But the area that I was in was a study of black holes and things like that. And observational data were starting to come in that were just shaking things up, discover quasars, pulsars, cosmic microwave background, and wrong evidence for gravitational waves, but the possibility that you might be able to do it. And so I quickly, as a postdoc, acquired a set of 5 superb PhD students who had come to Caltech wanting to work in one area of physics, fundamental particle physics, and immediately just gravitated over to me because here was another area that was just taking off. And I've seen this kind of thing happen in physics also elsewhere, that in unexpected areas, wonderful challenges arise, and huge progress can be made. And another example also that again comes from personal experiences in terms of technology, physics-based technology. In the period 1980, 81, 82, the foundations were laid at Caltech for 3 areas of technology. One is artificial intelligence. A guy named John Hopfield started developing at Caltech, artificial neural networks, which became the foundation for today's AI. Richard Feynman started thinking about quantum computing and the computers that are built on the laws of quantum mechanics instead of classical mechanics, and he saw that they would have capabilities that ordinary computers can't have. And one of my students, Carlton Caves, conceived of ways to make measurements, high technology measurements that would circumvent something called the uncertainty principle. And his ideas became the foundation for quantum precision measurement today, or quantum sensing. And this all came out of, in a period of just 3 years, the foundations. It's taken all these intervening time for these 3 areas to start to really blossom and appear out in the private sector. But things like that, and seeing them happen in my lifetime, and seeing them happen in periods when it appeared that there just wasn't much else interesting happening, it just makes me very optimistic on long time scales, as I say.
Okay, this was the wonderful final sentence. I want to thank you for your questions, and I think we all want to thank Kip Thorne for being here.